Hey everyone, and welcome back. So today we're going to do something new, and that's called a dependent source. So we're introducing a dependent source, and these are used significantly in modeling amplifiers, which we'll look at next time. And so let's just define this. It's a voltage or current source that has a value, value of the voltage or the value of the current that depends on a voltage or current somewhere else in the circuit. And so oftentimes this is over a resistor, and you're looking at the voltage over one resistor, and that value affects the value of the source that you're looking at. And so there's four configurations for this. You could have a voltage controlled voltage source, or VCVS. And so that means that the dependent voltage, which gets a symbol that's a diamond here, that's a voltage source, and it's controlled by the voltage across this resistor over here. And so it's going to have a scaled value of this voltage. And so we see Vx is right there, and we're scaling it by this factor A. So A times Vx is equal to what that source is going to provide, its voltage, Vy. So I rewrote it over here. Vy is A times Vx. And so they're the same voltage, except Vy is scaled by this factor A. And so in this way, this voltage Vy is controlled by the value of the voltage across Vx. So Vx isn't a source, so the voltage that appears across this resistor would be dependent upon whatever else is in that circuit. And so that's what makes this a little bit more complicated. And so if we solve for A, we can see that it's the ratio of these two voltages, Vy and Vx. So A is essentially how much bigger is Vy than, how many times bigger is Vy than Vx. And so these are two voltages, and so there's no unit here, and we call this value the voltage gain in this situation here. So let's look at the other configurations. We have a current-controlled voltage source, and so this is very similar. It's the voltage source here is dependent not on a voltage in your circuit, but a current somewhere in your circuit. And again, it's scaled by this factor A. And so here is an example. If I were using the current through this resistor, Ix, then I can find Vy as the product of A and Ix. So if I solve for, in this case, what A is, it is a ratio of a voltage over a current. And so this would have units of ohms, and this would be a resistance kind of value here, and it's called the trans resistance. And so this is the trans resistance multiplied by this I, so R times I gives us the voltage of that voltage source. Voltage controlled current source. So now this current source is the thing being controlled. And so it has the value Iy, and it's going to be a scaled version of the voltage somewhere else in the circuit. So there's Vx, so A times Vx. Again, if we put this and solve for the scale factor A, we can see that it's a current over voltage, and so that would have units of conductance, or Siemens, sorry, and it would be a conductance. So we call that a transconductance. And then lastly, a current-controlled current source. The current source is controlled by current through this resistor here. And so Iy is A times Ix. And so again, if we look at what A is, it's the ratio of two currents. And so we call this a current gain. How many times larger is Iy than Ix? So there is the introduction to dependent sources. Now we have to look at, well, how do we solve or analyze a circuit when a dependent source is included in that circuit? So I'm going to go through a few examples. Make sure you can see everything in view here. Great. The problem-solving process on this is less procedural because of the introduction of the dependent source. And so you're going to have to kind of look at the circuit and identify by inspection what tools you need to use. So by saying this, I'm saying you're not just going to just go to node voltage, or you're not going to just use Ohm's law, or you're going to find equivalent resistances, or you're going to do a Kirchhoff's current law or a Kirchhoff's voltage law. So you're going to have to look and think about what's going to help you get the answer that you need. Okay, so here's a couple examples to help you kind of see that problem-solving process. So here's two circuits, and they're not connected to each other except at one point, and that is ground. So you can see they're both attached to ground. So essentially these two points are connected together with a wire, if you want to think of it that way. I have a known voltage source Vs, so that's given, and it's an independent voltage source, circled, doesn't depend on anything. And then I have a resistor R1, which we would also know. So we would know pretty much everything going on in this circuit, given these two values here. And then we've defined a direction for a quantity I1. And what we've said here is that in the second circuit, there's a dependent current source that depends on the value of I1. And so here it is, it's A times I1. And then we have a known resistor R2. Now, the goal of this analysis is to find the value of the voltage V2. So we want the voltage right here across R2, and I can define a current entering the positive end of that resistor according to our labeling. So that is the goal. So let's just kind of go through what would we want to do. A good place to start is what you're looking for, V2, and write an expression with what's kind of surrounding that quantity. And so here I see V2, and I notice I can write an Ohm's law expression with R2 and I2. So I'm just going to start there. So V2 is I2, R2, and the directions all correspond to these being positive. So great. This is by Ohm's law. So I'm trying to find V2. I do already know R2. So now I'm just left with an unknown I2. So now I can expand and try to find I2. And so that's kind of the process that we're going to use here. And so looking at this circuit here, I noticed that by Kirchhoff's current law, that whatever current is entering this top node must be going through R2. So I2 is equal to this current AI1. So I2 is A times I1. And so then I'm just going to plug that back into my original Ohm's law for I2. So I got V2 is A times I1 times R2. A is a known, it's going to be a given in this circuit, and R2 is known. The only thing that we don't know now is I1. And so as you can see, this process then repeats itself. So I have to figure out what I1 is in terms of things that are known. And so looking at this first circuit now, we see I1, that's where it's located. And I notice this is a very simple circuit. It has a voltage source and a resistor, so we know that the current is going through this resistor is going to be related to these two with Ohm's law. But the current, according to this positive side here, if we say that this is the positive node and it has the value Vs, then we would generally write the current as flowing downward through this resistor. But our label shows it flowing upwards through this resistor. And so that's going to mean that the values negative of this, this current will be labeled negative because it goes in the opposite direction than we expected for this resistor. So I can write Ohm's law that I1 is negative Vs over R1. Another way, if that wasn't clear, to think about this, if I wanted to solve for this R1, I would take this node minus that node over R1. And that's 0 minus Vs over R1. And so we get minus Vs over R1, which is the same answer. So that's, again, we can substitute back in for I1. And so doing that, we get this final expression, V2 is negative A Vs times R2 over R1. And we know all of those values. So I left them in a general form where it's generic. These are unknown variables. But since we know these, then we know that we have the solution. If, sometimes it seems a little easier if you gave numbers to all of these and then kind of just solve it as an example, but I felt it was worthwhile to do this because we're going to do some algebraic manipulation in each of these examples. That's kind of the way that this is done. So let's go to one that's a little bit more complex. Here we have one circuit, and the dependent source is embedded in the circuit and with another independent source. So we have a a known independent source, voltage source right there, and there's ground on this bottom node. We have resistor R1, resistor R2, resistor R3, and we have this dependent current source, and it depends on this current I2 pointing upwards, so AI2 in that direction. And what the goal of this analysis is to find V out. So I want to find out what the voltage between these two terminals is. We need to find V out in terms of things that are known in the circuit. And so in this circuit, the knowns are the resistor values, the source voltage for the independent source, and the scaling factor, or in this case, the scaling factor, the current gain for this dependent current source. So I've written them down here. This is what we need our final expression to look like for V out. So again, we're going to start with V out. So what is V out? Well, I notice V out is the difference between this node and this node here, those two nodes, and that's also the voltage drop across R3. So V3 is V out, and they're parallel, so they should have the same voltage. And so V out is equal to V3. Using Ohm's law and these defined directions for I3 and V3, I can write that V3 is I3 times R3. And so we have V out is I3 times R3. We already know R3, so now I'm looking for I3. Well, I can see I3 is the current going down through resistor 3. There is no path down this terminal, and so whatever current is flowing in from the left into this node also flows down through the resistor 3. And that's our dependent current, A times I2. So I3 is A times I2, and I did that by KCL. And so I can plug that back in, and so I have V3 is A times I2 times R3. I know A, I know R3, I don't know I2, so we have to find an expression for I2. Well, here's I2, and so this is where it becomes, what do I do to find I2 in terms of things that we already know? And so good things to look at are Ohm's law, or if it's a current going into a node, we can do a KCL on that node. And so I'm gonna actually write a KCL on that node because I also know that this source voltage is a known, and I probably want to get that into our expressions because that's gonna have an effect on what this output voltage is. So by writing a KCL and using the Ohm's law version of that, I can access that VS. So here it is. So we got VB minus VS over R1 plus VB minus 0 over R2 plus the current going this way, which is AI2. That all has to equal 0. Okay. And then I'm also going to write another Ohm's law for the R2 resistor. And so VB, well, if I want to write it for I2 as it's defined here. So normally I would go VB minus 0 over R2 is equal to the current flowing down. But again, we're in this situation where this current is flowing up, labeled flowing up, and so we have to honor that. And so I'm going to do the expression backwards. I can write it as 0 minus VB over over R2 is equal to I2. And if I do that, it's the same as saying VB over R2 is minus I2. And so then we solve for VB here, and we get minus I2 times R2. So that's just Ohm's law using the direction of the I2 that was established originally in our circuit. Okay, so I can now, so in this expression, I didn't know what VB was. I know the source, that's known. R1 is known, R2 is known. We don't know what I2 is still. That's still something we're looking for. And now we don't know what VB is, but we have an expression that brings I2 into VB, and so that eliminates one of our unknowns, VB, and just leaves us with the one I2, okay? So plug that back in, and plug that in for VB. So I got minus I2 R2 minus VS over R1 minus I2 R2 over R2. That simplifies here because this ratio goes to 1, plus A times I2 equals 0. And then doing some more simplification here, I'm going to multiply everything by R1. And so we got negative I2 R2 minus VS, get rid of the R1 on that one, minus I2 times R1 plus AI2 times R1, that's equal to 0. So now I have an expression here that has only one unknown, I2, and I have an expression up here that has only one unknown, I2. So I'm going to solve this expression for I2 and then substitute it back in for our V out. So pulling out I2 and rearranging our terms, we get this expression here, and then dividing that factor timesing I2, dividing it by both sides, put it under VS, and I get this. I2 is VS over AR1 minus R1 minus R2. So now one step left, plug I2 back into our V out expression, and we have A times R3, then times this whole guy right here. So VS over AR1 minus R1 minus R2. So notice that in our expression, we know A, we know R, we know V, A, R, R, R. So we have all of these things known, so we are done, and we found V out. As you can see, this is a bit more complicated than what we've been doing, but you guys definitely have the tools to do this. And if you go down the wrong path, that's okay. You just gotta kind of continue to think about it and try something else. So, if Ohm's law didn't seem necessary and you couldn't get anything with it, did you try a KCL right here? Or you might have to do a KVL around one of these loops. And by doing all those things and just trying them, you can generate independent equations that are enough that we can solve for all of our unknowns. Last example. So in this last example, we're combining our Thevenin equivalent knowledge into something that has a dependent source. And I'm doing this because there's something about dependent sources that we haven't yet mentioned, and that you cannot turn them off. So we've turned off independent sources by shorting out voltages and opening up currents, but we can't do that with dependent sources. So if we were going to use the alternative method to find our Thevenin, we have to leave that dependent source in there. And so that's what this example is about. So let's go ahead and inspect our circuit. We have a voltage source independent, VS, right here. Our ground node is identified. We have a resistor R1, a resistor R2 to our output terminals here. And then we have this dependent current source that is dependent upon this current I1, so A times I1. So what is the Thevenin resistance for the Thevenin equivalent circuit for this original source circuit? So let's go ahead and use our alternative method. So in our alternative method, we short all independent sources, and in this case, we're shorting out the voltage source with we turn off all sources. Since we have a voltage source, we're going to short it. So I've replaced that with a short, and we're left with this circuit. Now, looking into the port, we can't just use resistor combining to find the Thevenin resistance here, because we have this source still part of our circuit. So the way to get around this is to imagine that we are connecting up a voltage source that has the value V test, and that will create a current that has the value I test, and then the resistance of the rest of the circuit would just be the ratio of these two, V test over I test. And that's, you can always think of that as what you're doing when you're finding the resistance looking into a port, but we're just being a little more explicit in our diagram. So we're going to connect that. So let's get started. I want our Thevenin in terms of V test and I test, so I got to find these two values. So let's start with the unknown node B and write a KCL and just see where that takes us. I know that I1 is going to be important in here, and so that's one of the variables we're going to want to kind of include in at least one of in both of our expressions so that we can eliminate it. So we need to have two expressions that have I1. So when I wrote my KCL here, I wrote it in terms of the currents coming in. We have I1 coming in, we have AI1 coming in, and then I test is coming in from this direction. So the sum of those three, I1 plus AI1 plus I test, is equal to 0. So this allows me to write an expression for I test in terms of I1. So I test is minus quantity A plus 1 multiplied by I1. Second, we also know that I1 here is part of the Ohm's law for R1. And so if I look at it, I can write that VB, so VB minus 0 over R1 is equal to negative I1 because it's going the other way. So if I would have to go 0 minus VB over R1 is equal to I1. And if I do that, we get this negative term in there. So VB is negative I1 times R1. This is similar to what was on the last example. All right, so I have this and I have this. There's still no V test in either of these expressions, and I need that. I don't know VB, so I have an unknown. I don't know I1, so I have that unknown. And I don't know I test, and also I don't know I1. So we can't combine these to solve for anything at this point. So what do? Well, I need to get V test into this an expression because I need that to find R Thevenin. So I have to use this voltage in some way. And so one way to do it is to write a KCL around this loop. And so that's what I'm going to do. I'm writing KCL around this loop. And so I have a voltage gain, V test, a voltage rise, and then I have the voltage drop across R2, and then the voltage drop across this dependent element. Well, the voltage drop across this element here is just VB minus 0. And then the voltage across this one, I can write it as an Ohm's law expression as I test, because that's the current going through here, times R2. So that's what I did. So we got V test is equal to the voltage drop I test R2 across this one, plus VB, the voltage drop across the bottom one. And so now I have a V test and an I test in my expression here, and I'm going to start to kind of combine these. So I'm going to combine this one with this one by taking this V test divided by that I test. It looks like we might be able to just substitute these in, but when we do that, we don't have enough information to kind of find our Thevenin. Might be able to find V test at this point, but there's a couple ways to go from here. But the way I chose to do it is to just now go back to R Thevenin. R Thevenin is V test over I test, so that's this expression. I test R2 plus VB, that's V test, over I test, which is this expression, minus A plus 1 times I1. And so now we have this. We still have VB is unknown, and I1 is unknown, and I test is unknown. But I can start to see something showing up here. I test has I1 in it, and VB has I1 in it, so we might be able to eliminate that when we substitute, and indeed that's what happens. So let's substitute some more. So I test, I'm going to resubstitute it in for this expression here, so minus A plus 1 times I1. That's multiplied by R2 now, right? And then I'm going to substitute negative I1 R1 for VB, and then we have our same denominator. So notice I1 appears in each of these terms. Actually, negative I1 appears in each of these terms. So I'm going to pull that out. Minus I1, and we're left with this expression on top. And if I pull out minus 1 on the bottom, we're left with this expression on the bottom. And these drop out to 1. And so notice then we know A, we know R, and we know this R. So I found the Thevenin resistance. I know it looks complicated, and it is. And it takes practice, but I want to bring you guys up to the next level, especially when there's consequences are kind of, really small right now. So you can try it, and if you don't get it correct, that's fine, but at least you're experimenting with it. All right, thanks a lot for listening.